Greetings. Now that we have developed an equation for the second law of thermodynamics, which tells us which process is possible and which process is impossible, we are in a very good position to use all three equations, namely the mass conservation equation, the energy equation, and the equation for the second law of thermodynamics to solve another problem and see how these equations individually and in combination work. The problem that I want to solve I've selected from the book, the thermodynamics book by Turns. I've introduced my references in the first lecture, in the first problem, and I repeat referencing the books that I like so that you could also use them and learn better from them. So the problem that I have selected to solve, and I use the numbers initially and then would develop on that problem to learn further and learn better, is a problem that tells us we have superheated water. We have a piston cylinder first. This is a piston cylinder. Okay. This is a piston cylinder, and what we have in it, we have superheated water. M equals 2.5 kilograms. That is the mass of water. And then the initial condition of water is in the initial condition. Pressure is 300 kilopascals and temperature is 500 Kelvin. These are our initial conditions. Now, the problem tells us that we compress this superheated water to saturated water vapor in a reversible isothermal process. So the final condition what is the final condition? The process isothermal, so T equals 500 kelvins, and it is saturated water vapor, so X equals 1, and that is the final condition. Now, we have both initial and final conditions, but we are given another information. And that information is that the process is reversible. The process is reversible. Process is reversible. And that means Sgen equals 0. Okay. Determine the work required to compress the water and the heat transfer during the process. So what is asked from us is that how much work should we do and how much heat transfer would we have. So this is all what we want from the problem. and the problem wants from us. Look, it is a very important step to be able to turn this definition that you see, this writing, this physical description that you see, into something that is a thermodynamic language. Just doing this step, what I have done, I have selected properties, defined an initial condition, defined a final condition, and defined something about the process. You see, these three are the three items that define the process. And these are properties for initial and final conditions. And it is very important that you should be able to translate this language of the description, of the physical description, into this writing, initial condition, final condition, and the process, and then continue with it to calculate all the steps that I have said, and now I repeat. Those steps are: one, find the properties, find all properties. Two, draw a diagram. Three, simplify equations. For the problem at hand. And do all this for a defined control volume. So what you have to do initially is to define the boundary, for your solution. This is very, very important that you define the boundary and then do all these things that I have said. And then, which is a step, you call it four. And I quite easily interchange these steps and perhaps do one of them um, halfway through and then return to it and complete it. And then five, combine all towards a solution. These are the steps that we shall take. So let's do the first step and define a boundary for our study. And the boundary I define is, for the time being, is the steam inside the piston cylinder. Okay, this is the boundary I select for the time being. And since the problem is isothermal, the temperature of this boundary, T equals 500 kelvins throughout the problem, throughout the solution, in fact, for the time being. So this is 500 kelvins, and this is the temperature of the boundary that we have selected. This boundary, there's an exchange through this boundary of work, and heat transfer. So what we do, find all properties. So for the initial condition, we have call it condition 1, call it condition 1, and what we have is P equals 300 kilopascals and T equals 500 Kelvin. What we do is go to the tables or to our application and try to read the properties. What I have read from my application is that V, a specific volume, V1, let's call it from here, is 0.76 cubic meters per kilograms. U1 equals 2693 kilojoules per kilograms. H1 is 2920 kilojoules per kilograms, and S1 is 7.426 kilojoules per kilograms Kelvin. How did we learn the property entropy? You see, the third law of thermodynamics tells us what the basis for entropy is, where the entropy is zero, and how it is it. I won't go into that law now. That is something for later on. But we can find properties uh, of saturated material, like saturated water, like R134A, and else in tables, and entropies are also written there. So just like whatever property of water that we read from the table, entropy is also the same. So for condition 1, we have all the properties. Now let's go to condition 2. Condition 2, and we know that temperature is also 500 kelvins and x equals 1. And therefore, to find the properties in a very similar manner, we go to the tables, and what we read is that Psat equals 2638.9 kilopascals. So during the process, we have compressed saturated water or superheated water from 300 kilopascals to 2638.9 kilopascals. V, a specific volume, is 0.0758 cubic meters per kilograms. U is 2602.6 kilojoules per kilogram. H is 2802.6 kilojoules per kilogram, and S entropy is 6.2354 kilojoules per kilogram. And these are the properties, all the properties for initial and final points. Now, the next step for us should be to draw a diagram. We may draw the diagram for any two properties, while we have just learned about entropy. We may also use it for drawing our diagram. Let's see. Let this be a TS diagram. TS diagram. T is in kelvins, and S is in kilojoules per kilogram Kelvin. Now, saturation line looks fairly similar to what we had for TB diagram, except the fact that the slope is sharper. The slope is not as gentle as it should be in the TB diagram. You see, if we wanted to draw a TB diagram, V2 is 0.075 and V is 0.76. So, in fact, between 1 and 2, there should be 10 times difference. Now, while we are drawing the TS diagram, the difference is 6.23 and 7.42. So it's more manageable, and what we would draw would be more realistic. Now, this is the line for 500 Kelvin. This is the line for 500 Kelvins, and this is the constant pressure line for saturation condition, which we have learned is 2638.9. P equals 2638.9 kilopascals, but the initial condition is somewhat different, which is on this line, and the saturation pressure and the pressure on this line, P equals 300 kilopascals. This is 0.1 and this is 0.2. And our process is isothermal. So regardless of any combination that happens between these three, our initial point is here, our final point is here, and the process is over this line, regardless of any combination that happens between these three. And that's a very important point. In fact, we shall see shortly that if the process is not reversible, then we would have different combinations of work and heat. So, for the time being, this is a good position. Look, this is S for 0.1, and so for 0.1 S is 7.426, and the unit for S is kilojoules per kilograms Kelvin, and for 0.2 S is 6.2354, 6.2354, and the unit is kilojoules per kilograms Kelvin. So we have these 2 points, we know the process, and now we are in a very good position to simplify all our equations for this problem. Our equations, where are our equations? These are our equations. dmCv by dt is mi minus me, m dot I minus m dot e. Now, the problem has a certain initial and a final position, and therefore we may integrate it between initial and final conditions. There are no entry or exit mass, therefore we may easily simplify this equation to m2 m2 minus m1 equals 0. And therefore the 2.5 kilogram mass would remain constant and would stay in the cylinder. So M2 equals M1 and equals 2.5 kilograms. Now, let's move to the first law of thermodynamics. The first law tells us there is no incoming mass, there is no exit mass, there are both heat and work, and also there are initial and final conditions which we should also take care of and integrate in our equation between these two conditions. So what we would do now, it would look like this. M2U2 minus M1U1. We have ignored all changes in velocity or elevation, and that would equal no mass in, no mass out. Therefore, it would be Q12 minus W12, and that is the first law of thermodynamics. Now, let's move to the second law of thermodynamics. There is no mass in, there is no mass entering, no mass going out. The problem tells us that the process is reversible, so S dot gen is 0, and therefore the change of entropy inside our boundary would be a function of only this term, and these three terms would all be 0. So what I would write is M2S2 M2S2 minus M1S1 equals Q12 divided by TB, the temperature of the boundary. Now, we are in a very good position to solve this equation and put numbers to it. I would keep writing in the same page since it would give us everything together. I could change pages, easily, but we wouldn't have everything in the same picture. So, mass is 2.4 kilograms, so 2.5 kilograms times U2 minus U1, which would be 2602.6 minus 2.5 times 2693.0 equals Q12 minus W12. And that is the first law of thermodynamics. Now, the second law may be written in a similar manner. 2.5 times 6.2354 minus 2.5 times 7.426 equals Q12 divided by 500. These two equations simply give us a very simple answer, and that is Q12 equals minus 1488.25 kilojoules, and W12 equals minus 1262.25 kilojoules. Okay, now we have to discuss this answer and see what it tells us. We are now in a very good position to discuss the results we have already calculated. Look, this is the work done. It is telling us that 1262 kilojoules of work is done reversibly. That means that could well mean that we have pressured this piston to go down, compress the vapor inside the cylinder, and bring it to the saturation vapor condition. But at the same time, while we have done 1262 kilojoules of work, the cylinder has lost, or better say, the vapor has lost 1488 kilojoules of heat. It means that we have given 1262 kilojoules of work and have caused 1488.25 kilojoules of heat to go out of the cylinder. So in fact, the cylinder has lost more energy than what he has gained. Where does the rest of energy has come from? You see, the internal energy of the vapor inside the cylinder has dropped. How much has it dropped? It is this, the left-hand side of this equation equals minus 226 kilojoules. So by compressing this vapor, although we have done it reversibly, we have not only lost all the energy that we had put in, but we have caused some of the energy of the vapor itself to go out in terms of heat transfer. Now, there are two ways to extend this problem. The first point that you have to look at is that although this problem inside the boundary we have defined is reversible, but we all know that if heat transfer occurs, there must be a temperature difference. So there is perhaps a surrounding, and just please extend this line to all around the cylinder. There is a surrounding at, say, T equals 25 degrees C or 298 K. Assume that there is such a surrounding and heat is transferred from the cylinder to the surrounding, and then from it to the general outer surrounding. This process inside this close proximity, inside this near surrounding, is irreversible because it is heat transfer across the temperature difference. Well, how do we calculate that? It is informative just to do some calculation on it because the second law of thermodynamics, well, the first law of thermodynamics and mass conservation law don't tell us much about the surrounding. Let's see, this is the surrounding, the near surroundings, and there is certain boundary here which goes around. Say, if I want to draw this boundary, I would do it like this. I would do it like this. And this is our near surrounding. And please coincide these two boundaries because they are both the same thing. So there is no mass going in and going out. So M2 equals M1 for the near surrounding, and this is, say, the air near that cylinder. The energy inside it doesn't change. It's only any heat that enters the surrounding from the cylinder just leaves it through the other side, through the other boundary, to the larger surrounding. So 0 would equal Q12 plus Q12 in plus Q12 out. And it is the same Q12 that we have calculated here that goes in is positive here. For this surrounding is positive, and this one is negative. So it makes, and there's no work with it. So what it tells us is that Q Q12 in equals Q12 out, and that would equal, in fact, one is positive, the other is negative, so I have to write it in absolute terms, 1488.25 kilojoules. Depending, the negative or positive signs are decided depending whether you want to look at the Q entering this near surrounding or the Q leaving this near surrounding. But the second law of thermodynamics tells us that 0 is Q12 divided by 500, which is the temperature at this boundary, plus the same Q12 divided by 298 and plus S gen, which is the generated entropy here. You see, this is what we mean by internally reversible. It means that this process was internally reversible, but there were irreversibilities outside. So we have a value for Q, and therefore we could calculate S gen, and that would equal 2.0176 kilojoules per Kelvin. And this is the entropy that is generated because of this process, just outside the boundaries of the cylinder. Okay, so you see, Once we change our boundaries, then the whole thing changes. If we stick to the boundary inside the cylinder, then it is reversible. The SGN would be zero. But for a different boundary, there is entropy generation and there are irreversibilities. There's heat transfer across some temperature difference, and so it generates entropy. Okay, now look, uh, we return to the piston cylinder case, and what I want to show you once again is this equation. This set of equations. And what does it tell us? It tells us that the change of a property inside the controlled volume or the boundary under study, whether it's a controlled volume or a system, is a function of that property going in and that property going out. So these terms are all properties, are point properties. And there are three further terms: heat transfer, work, and entropy generation. And this is exactly what we have studied in this example. We assumed Sgen to be zero, and then we calculated both Q and W since we have two equations and two unknowns. This was a very good pattern. We had two equations, two unknowns, and there were three properties of the process, not of the point properties, not of the system, but of the process. We assumed one property to be zero, and then we calculated the other two for known initial and final conditions. So all initial and final conditions were known. Okay, now I want to do something else. I want to assume that there is some irreversibility in the process. Okay, I want to assume that there is some irreversibility in the process. And since I have to make some assumption, what I would do is that I would say, assume that we do the process with this amount of irreversibility inside our cylinder. How? Very simple. We did work in the reversible case by just pushing the piston down. Okay, that was the work that was done, and this work was done reversibly. Now, I want to do another form of work, which is a propeller. Look, assume that we were to solve this problem. We were to solve the same problem, and the work was not done by just pushing a piston down, but there was a propeller, and this propeller was irreversible. Why? Because the propeller has to have some friction with the vapor. If there is no friction, then no work could be conveyed from the propeller to the vapor. There has to be some friction, and that friction generates entropy. And for the sake of simplicity, I would assume that in this second case, the entropy generated would be this one. I would use the same number for the generated entropy. I would try to see what would happen if this was the case. So our equations are just as before, And I would write everything down in green just to make it different. What would happen? The first, we are keeping the initial and final points the same. If that is the case, then first law of thermodynamics would remain the same, although numbers for Q and W would change. And the second law of thermodynamics would be the same, except that there would be an S gen added to this term. Because why? Because of the propeller. Because of the propeller, which is producing this S gen. So now we have an S gen which equals 2.0176. We have a Q12, which we don't know what it is, but we are in a good position to calculate it. And we have W12, which we don't know what it is, and we just wish to calculate it. How do we do that? Very, very simple. The two equations that we write are just similar to what we have here. You see, let's fold paper to be able to show the equations. The first law of thermodynamics would still be very similar. M2 U2 minus M1 U1 equals Q12 minus W12. And the second law would be M2 S2 minus M1 S1 equals Q12 over TB plus SG. And what I want to do right now is to put numbers to these equations. The first equation would tell us the first equation would be 2.5 times 2602.6 minus 2693.0 equals Q12 minus W12. The green are our new condition where we do work with this propeller and we impart S gen 2.0176 kilojoules per Kelvin of entropy is generated with this propeller. And the second law would be 2.5 times 6.2354 minus 7.426, and that would equal Q12, which has a new value, divided by 500, plus Sgen, which is 2.0176. And we get two answers, one for Q12, which would be minus 2497.05, and the other would be for W12, which is minus 2271.05, and both are in kilojoules. Do you remember the values we had in the previous case? In the previous case, where it was reversible, we had only done 1262 kilojoules of work. Now, which is irreversible, we have done 2271 kilojoules. You see, the initial and end points are the same. They haven't changed. We have moved from this one to this one. The process, at least as far as the one property was concerned, was the same. It was an isothermal process. So if we wish to draw the green process, the new process, we would still start from the same point, end over the same point, and draw over the same line. But you see, the irreversible process requires more work and also delivers more heat to the surrounding. And this is a pattern which we shall discuss it later on in more detail. It means that if the work is to be negative, it means that if we have to give reversible process would require minimum work. So for negative work, irreversible process, for reversible process, reversible process requires minimum work. Minimum work. So if we are to do work for reversible process, work is minimum. And that's good for pumps and compressors. And all other instruments like fans, ventilators, and all other instruments where we have to do work. Minimum work is for reversible process. And that's why it's a valuable point. See, when estrogen is zero, it gives you minimum process. And that's where you can refer to. That's the that could be a baseline where we can compare all possible processes to that point and decide how far we are. That's the point. That gives you the minimum work, and then for a real process like this yellow green one, you have more work, and now you have a basis that you can know how far from ideal process you are. That's very, very important aspect of the second law of thermodynamics. There is still one further point which I want to use this problem to express this. A further intriguing point with this problem is that we calculated work without resorting to the very famous equation of integral P dV. So you well know that could we could have written work equals integral P dV, and that work is valid for a reversible process on a cylinder piston arrangement. So this work should be really equal the integral P dV. To that end, let us draw a PV diagram. This is V. This is P. This is the saturation line, and the main line that we are interested in is the temperature line for 500 kelvins. So this is 500 kelvins, and the pressure on this line, P equals 2638.9 kilopascals. And there's another pressure for this problem, which is this line, say, this pressure line P equals 300 kilopascals. Point 1 is here, and point 2 is here. And we have all properties for points 1 and 2, and our process is this one. So if this be the case, then for a reversible process, work should be the area under the PV diagram. So this should be work. And the green area should give us work. In fact, the green area should be exactly equal to 1262. There is a point in this problem which we have to note. Since work is done on the cylinder, on the piston, and the work is done on this vapor, therefore the pressure inside should be accounted for. We have to use pressure inside the cylinder in this equation. So our pressure is changing. A question I want to answer and just bring your attention to is that this line is a straight line, a good approximation for this line, for this constant temperature line? Is it a good approximation? And to answer this, all I need to do is to calculate work from this equation. W would be, or W would be M times W between 1 and 2. And this would equal, if this was the straight line, we could write this would be P1 plus P2 divided by 2 times V2 minus V1 and times M. This should be the equation that would give us the area underneath, if and only if this line is a straight line. So for a straight line, if this line is a straight line, and if you put values to it, this would equal, you see, 300 plus 2638.9 divided by 2 times V2, which is 0.0758 minus 0.76 and times 2.5. And the answer this would give us is a surprising one. It is minus 2513.5. What is it telling us? It is telling us that if you assume this line to be a straight line, we would calculate a far larger area underneath a constant temperature line than what we should really do. This is the area. This is the true answer. This is the correct answer. And this answer is not just correct. What I did, just to show this point further, was to select the 1500 kilopascal line. This line is, say, 1500 kilopascals, and assume that there is a straight line between points 2 and 3, and there's a straight line between points 1 and 3. So basically, instead of approximating a curve with a straight line, what I did, this is 1, this is 3, this is 2, this is point 2. I said, well, I would take a middle point and approximate it with this line and this line. And what I expect is that the area underneath would be smaller. The area underneath these curves with straight lines should be smaller. And that is exactly what happens. I did calculate this and found out that the work would reduce to minus 1735.9 kilojoules. A far better approximation to this one than this one. And if we take all these points along this curve, all the points along this curve, and use infinite number of straight lines, then the answer we would get should be 1262.25. Another assumption which I tested here, and it is worth knowing, is that could you assume that on this constant temperature line and this area, vapor is perfect gas? Okay, so we were two assumptions. First is T equals CTE, a straight line. This is our first assumption. And the second assumption is vapor perfect gas. If it is perfect gas, then PV equals RT, and that would give us that PV equals constant. We just have to insert this equation into this one, is do the work here, and calculate the result. And the result would be W12 would equal minus 1314 kilojoules. Compare it with 1262, and you would see that the perfect gas assumption is a far better assumption than just assuming that this line is a straight line. Whether we are allowed to do these assumptions or not depends on the application that we are concerned with and how much accuracy we require. But at least we know that different assumptions could bring us to different results, and some are better, some are worse. Thank you very much for listening to this problem, to this solution, and all different variations. And cheers